couple of spots in the Krebs cycle. It depends on the structure of the amino acid. Once you remove the amino group, it becomes something else. So for example, you deaminate alanine, you've got pyruvic acid. Okay? And alanine is a very common amino acid. So what I've just described allows us to do what? We have protein, we have hydrolysis of the protein, and we get amino acids, right? And then we have oxidative deamination, and then where do the keto acids go? Glycolysis, pyruvate, Krebs cycle, and we can get ATP then from protein, can't we? So can you see where we are now with my chart? We've linked protein, carbohydrate, and lipid catabolism, haven't we? And we've linked lipid anabolism, the synthesis of lipids from this. Can we also link protein anabolism in this way? You bet. Because we can pull out these organic acids in this way. Notice the arrow goes both ways, it's a reversible reaction. So we can pull out those organic acids. If I have now a keto acid from Krebs, I join that in a transamination reaction, and I can build an amino acid. This is an anabolic reaction. If I join amino acids together in what we call protein synthesis, clearly protein synthesis is an anabolic process. What we have on the board here is, some of you may prefer this, I don't know, but it's, in essence, this is the outline on the chalkboard of this, and we have combined protein catabolism and anabolism, carbohydrate catabolism, lipid catabolism and anabolism, and then we also talked about how we could get, or I'm going to talk about it right now, it's possible to take lipids and even amino acids and manufacture sugar, although it's a backdoor play metabolically. You can do that because when you are starving, your brain still wants that glucose, and you're going to find a backdoor play to make it, and that can happen as well. Of course, glucose into glycogen, that's also anabolism. So we have some interesting pathways here. Glycolysis and the Krebs cycle can be both catabolic and anabolic. They can function in both ways. So if you think about it, the pathway which can function in anabolism and catabolism, we call it amphibolic pathway. Both catabolism, which is a breakdown reaction, and anabolism, which is a synthetic reaction. Example of amphibolic pathways: glycolysis, Krebs cycle, these are actually amphibolic pathways. So if you're ever bored, you can come out to Sequoia 1 when there's no class. You can check out glycolysis, a number of these reactions are reversible. They can go down or they can go up. The Krebs cycle, we can put in, out, we can pull out, so that we have both catabolic and anabolic syntheses, joining forces. And that's one of the reasons why in this chart, the glycolysis and Krebs pathways are in the middle. So not only is pyruvic acid the hub of carbohydrate metabolism, it is in many ways the hub of the metabolism for many other metabolites in the cell. All right, I'm going to continue to leave that up there. And I want to list now the blood-borne energy ingredients for various tissues. The relative importance of blood-borne energy carriers. So what you have different tissues that prefer different sources of energy. That's the reality. And so if we list, for example, the brain, it turns out that the brain has an almost absolute requirement for glucose. The brain has a sweet tooth, doesn't it? And if we look at skeletal muscle that is exercising, so exercising skeletal muscle. Here's the picture. It changes. Initially, skeletal muscle uses sugar. It uses carbohydrate, typically glucose. So initially, glucose. But later, after say 15 or 20 minutes, what does skeletal muscle prefer? It shifts to fatty acids. After 20 minutes, so if you want to burn fat, it's important to have an extended period of exercise, isn't it? Because if you just work out for 15 minutes, what are you going to do? You're going to just use up some glucose, which is not the end of the world. You know, it uses up some calories. But if you're going after burning some fat, then we need a little longer time. So first, we have glycogen lysis. What is glycogen lysis? Splitting glycogen, right? Glycogen to glucose. Then, we're going to split fats. What are we going to call that? You got it. Lipolysis. So first glycogen lysis, then lipolysis. That's what happens here with the exercising skeletal muscle. Now what about in a couch potato? We're just sitting there watching the Super Bowl or maybe reading Winter and Traffic, whatever, studying. And then we have resting skeletal muscle, right? So the resting skeletal muscle is different than exercising skeletal muscle. Resting skeletal muscle is like the liver, and it's like cardiac muscle. These tissues utilize fatty acids. Now, of course, it turns out that resting skeletal muscle doesn't use nearly as much ATP as exercising skeletal muscle, right? So the relative quantities are not going to be balanced. But still, they're going to prefer fatty acids as fuel. We're also seeing that some recent research is showing that some tissues, especially after training, can become trained to utilize lactic acid as a fuel. It doesn't have to be processed necessarily.